Section 2.4, functions. We're going to talk about relations and functions, graphing them, how to determine if something is a function. We're going to talk about range and domains of functions and any range and domains of relations. So any set of ordered pairs is called a relation. The set of all first components is called the domain of the relation. The set of second components is called the range of the relation. A function is a rule that assigns to every element in a set X exactly one element in a set Y. So if I have something in my set, I don't know, 1, 2, 3, and I have a set 4, 5, 6. For my X, this is my domain. This is my Y, or my range. Okay? So my domain is 1, 2, 3 in this example. My range is 4, 5, 6. For every X, there's only one Y assigned to it. Okay? I could do that. I could do that. Okay? That right there is a function. As soon as I do something like this, that now is not a function, because for the number 2, I have 2 different Y's associated to it. Okay? So we will treat a function as a set of ordered pairs, X comma Y, where X is a domain and Y is a range. The notation, function notation, instead of Y, we'll say f of x. So remember, domain, x's, range, y's. So I have some function. Let's say f of x is equal to 2x plus 3. So I have some input value. Say x is equal to 1. X is equal to 1 is my input value. It is my independent variable. X is my independent variable. I put that 1 into that rule, so 2 times 1 plus 3, and I get out of it a 5. So what I get out, the f of x, the y is my dependent, the x, what I put in, is my independent. So I'm putting an independent variable x into it, I'm getting my dependent f of x. It's dependent on the value of x. I have 3 functions here. F of x is equal to x cubed minus 3x plus 1. G of x is equal to 2 over the square root of x. H of x is equal to square root of 2 minus x. Remember, if I have some function here, let's say f of x. I'm just going to write f of something. F of x is equal to x cubed minus 3x plus 1. F of whatever I want here. I could put an x in there, I could put a 7 in there, I could put x plus 5 in there. I will put in wherever there's an x. Okay? If I have f of x plus 1, then I would put x plus 1 wherever there was an x. So that's how you work with functions. So I want f of negative 1. So wherever there's an x, I'm going to put a negative 1. So I have negative 1 cubed minus 3 times negative 1 plus 1. Negative 1, this ends up being plus 3 plus 1, which gives you 3. In my g function, I'm going to put in 0 wherever there's an x. 0 on the denominator is undefined, so this is undefined. In my h function, wherever I have an x, I'm putting in a 0. So that's just the square root of 2. In my f function, wherever I have an x, I'm putting in an a. So instead of x cubed, I have a cubed minus 3a plus 1. In my f function, wherever I have an x, I'm going to put in a negative x. So I have negative x cubed plus 3x plus 1. So this is working with functions and the function notation. I want the domain of f of x is equal to 3 over x plus 5. Domain are my valid x's. So remember, in a fraction, we cannot have this bottom equaling 0. So x minus 5 cannot equal 0. If x minus 5 cannot equal 0, that means x cannot equal 5. So the function does not exist when x is equal to 5 because it makes the denominator 0. The domain, let me graph it first so you can see what the domain is. This is what the graph looks like. With that number being 5. It can't be 5, it could be anything else. So reading this graph from left to right, it goes from negative infinity to 5. It does not include 5, union 5 to infinity. So there's the domain. So this is the domain in interval notation. I think it's easiest to graph it first, and then once you graph it, to write the interval notation. Another one I want to find the domain for. Square root. Remember square roots. If you have a negative under the square roots, it's imaginary. So 4 minus x cannot equal a negative number. So it must be greater than 0. Okay? So there's what I want to solve. So I'm going to add x to each side. So I have 4 is greater than or equal to x. Or I could write it as x is less than or equal to 4. Okay? Picture of it. There's 4, it can equal 4, less than. So interval notation of the domain would be negative infinity to 4. So there's my domain in interval notation. In set notation, it's a set of all x such that x is less than or equal to 4. 0 of a function, you need to know what a 0 of a function is. And the 0 is defined when f of x is equal to 0, or my y is equal to 0. So my 4 minus x, my f of x is equal to 0, If I were going to solve that, square both sides, so you have 4 minus x is equal to 0. So x is equal to 4. So the 0 is 4. The range, my output, from a square root. Remember your output. I won't get negative numbers out of the square root. If x were 4, I'd get a 0 out of it. If x were 3, I'd get a 1 out of it. So my range is greater than or equal to 0. My f of x is greater than or equal to 0. Or, if that's 0, this is what the graph looks like. It's from 0 to positive infinity in interval notation. Domain and range of graphs. When you look at them, domain and range. A domain, you're looking at the x value, so you're looking at it from left to right. The domain is found by looking at the graph from left to right. The range, you're looking up and down. And really, I say top to bottom, but it's really bottom to top because it's smallest number to largest number. Smallest number to largest number. So if you look at the graph from left to right, you can see this way would be my domain. And I start at -1, and it includes -1. It's solid. And it goes to +1. So there's my domain. My range, I'm looking up and down. So my smallest number is 0, and it includes 0. And I go all the way up to 1. So this is my range. Okay? So my domain goes from -1 to +1, inclusive. My range goes from 0 to 1, inclusive. And if you want other notation for it, I said it started at -1, ended at +1. So you can write -1 is less than or equal to x is less than or equal to 1. Or all the set of x such that -1 is less than or equal to x is less than or equal to 1. Graphing top to bottom or bottom to top, low point 0, high points 1. So 1 to 0 it is, 0 to 1. So 0 is less than or equal to, y is less than or equal to 1. Or you could write f of x there. Or set notation y such that 0 is less than or equal to y is less than or equal to 1. So that's looking at a graph finding domain and range. Let's do this one. Domain, left to right. If I go this way, all the way. I hope you can see that it's going up, but it's also going to the left. So it's going to negative infinity. Going that way, but it's also going up, but all the way to the right. Positive infinity. There's your domain. Range. Remember, up and down I'm looking at it. So my smallest number for my range is 0, but it goes up to positive infinity. The graph above has a domain that's all real numbers, negative infinity, positive infinity. The range of the function is y is greater than or equal to 0. Low point 0, high point not infinity, goes forever. Functions. We can represent them as ordered pairs. We can represent them as tables, graphs, equations. There's so many ways to look at functions. One way is the ordered pair. And remember, a function for one x, there's only one y. So let's see, is this a function? What's the domain? What's the range? Domain would be my first values. Domain. So ABC, the set of ABC. Range, D again, you don't have to list it twice, list it once, and E. So D and E are my range. And for A, there's only one assigned to it, it's a D. For B, the only thing assigned to it is D, and C, the only thing assigned to it is E. So this is a function. Domain, 1, 2, and 3. Range, A, B, C, D. One has A assigned to it, one also has B assigned to it. So this is not a function. Because one is assigned to A, one also has a B. Not a function. You can look at it as a table. Domain would be 0, 4, and 7. Range, -3, -2, 1, 1, 2. Is this a function? I'm circling stuff so you can see, is that a function? And hopefully you're saying to yourself, no, it is not a function. Because 0 has 1 or -1 assigned to it, 4 has plus or minus 2, 7 has 2 and -3. So it's not a function. Not a function. You can use equation as examples. If you have an equation, solve for y first. So if I solve for y, I take the square root of each side. And when I take the square root of y squared, I have y. When I take the square root of x, I have the square root of x, but plus or minus, because I'm going to be positive square root of x minus square root of x. Okay? So for example, if x were 1, y could be 1, but y could also be -1. So this is not a function. Because for one x of 1, I have two different y's, plus or minus 1 is assigned to it. But this one is a function. This one is a function. So if you see a y squared in it, it won't be a function. Okay? You can look at graphs and say, okay, is this a function or not? There's something called the vertical line test. Okay? So to determine if a graph's a function or not, we can use a vertical line test. If no vertical line crosses the graph more than once, then the graph is a function. So I have some graphs here. And let me put a line here too. Let me find a line to put there. There's a line. There's my line I want to use. Okay. So I have a line. And notice if I take, whoops, hold on. Take my pointer. I want to get rid of that line. Okay. Get rid of that little line and let's move that over. And let's get rid of this little line because I don't know what happened there. There, cut it. Okay. So I have a line here. If I take this line, if I drag it across my graph, if it crosses the graph more than once, then it's not a function. If it only crosses once, it is a function. So this one, you can see there are spots where it crosses twice. So this is not a function. This one, again, not a function. The next one you might need to write on your graph a little better because I made a real light color and I don't think it graphed. It's a semicircle. Okay? Half a circle. That is a function. And then the last one is a function. Okay, so the first two are not functions. The last two are functions. Okay? 2-4 homework we will do in class the next day.